May 24, 1941, 6 p.m., Denmark Strait, North Atlantic. HMS Hood, flagship of the Royal Navy and the largest warship in the world, closed to engagement range with the German battleship Bismarck. The range was 26,000 yards, over 14 miles of open ocean separating two steel fortresses designed to destroy each other through mathematics and metallurgy. Hood's forward 15-inch guns fired. 8 seconds later, Bismarck's fifth salvo landed. One shell, possibly two, struck Hood near the mainmast. The shells, each weighing 1,764 pounds, traveling at 2,960 feet per second, carrying 110 pounds of high explosive, penetrated Hood's deck armor, detonated inside a magazine containing 112 tons of cordite propellant, and triggered a catastrophic explosion that broke the ship in half. 3 minutes and 40 seconds after the first salvo, Hood was gone. 1,415 men died. 3 survived. The shell that killed Hood represented the culmination of 50 years of naval ordnance engineering, a weapon designed to fly through the air for miles, penetrate the thickest armor ever manufactured, and explode inside the target with enough force to destroy any structure humans could build. The story begins not with naval warfare, but with physics problems that seemed unsolvable in 1890. How to make steel hard enough to penetrate armor but not so brittle that it shattered on impact, and how to make explosive charges powerful enough to destroy armored compartments but stable enough to survive being fired from guns. The naval shell that dominated World War II battleship combat was the armor-piercing capped round, typically weighing between 1,700 and 3,200 pounds, depending on caliber. Constructed from specially treated steel capable of withstanding impact forces exceeding 50,000 pounds per square inch, filled with explosives timed to detonate after penetration, and fired at muzzle velocities approaching 3,000 feet per second. The engineering required to create these weapons represented some of the most sophisticated metallurgy and explosive chemistry of the industrial age. The shells weren't simple projectiles, they were complex mechanical devices with multiple components serving specific functions. The armor-piercing cap protected the pointed nose from shattering on impact. The ballistic cap improved aerodynamics during flight. The body, forged from nickel-chrome molybdenum steel and heat-treated to specific hardness gradients, provided penetration capability. The base plug secured the explosive charge. The fuse, typically mounted in the base, delayed detonation after penetration. And the bursting charge, picric acid, TNT, or later formulations, provided the explosive force that destroyed the target from inside. The design solved problems that had defeated earlier naval ordnance. Solid shot, used through the early 1900s, could penetrate armor but caused limited internal damage. Explosive shells with impact fuses detonated on contact, wasting explosive energy against external armor rather than internal structure. The armor-piercing shell with a delayed fuse combined penetration with internal explosion, maximizing damage against the most heavily protected warships ever built. The development history is traced through naval arms races that defined pre-World War I great power competition. Britain, as the dominant naval power, drove initial development. Germany, challenging British supremacy, forced accelerated innovation. The United States, building a modern navy, contributed metallurgical advances. Japan, constructing a fleet to dominate the Pacific, refined explosive formulations. By 1939, all major naval powers possessed armor-piercing shells capable of penetrating any armor at combat ranges, creating offensive capabilities that exceeded defensive protection. The British 15-inch Mark 17 shell, typical of World War II armor-piercing rounds, weighed 1,938 pounds. The shell body, 60 inches long and 15 inches in diameter, was forged from nickel-chrome steel heated to 1,700 degrees Fahrenheit, then quench-hardened in oil. The process created steel with compressive strength exceeding 85,000 pounds per square inch, harder than any commercial steel but carefully controlled to avoid excessive brittleness that would cause the shell to shatter on impact. The metallurgy was extraordinarily precise. The shell needed to be hard enough at the nose to penetrate face-hardened armor, but tough enough in the body to resist fragmenting from impact shock. The solution was differential heat treatment that created hardness gradients. The nose received maximum hardening, the body received moderate hardening. The base, which never contacted armor, remained relatively soft to absorb explosive forces from the bursting charge without fragmenting prematurely. The armor-piercing cap, a separate steel component attached to the nose, served a counterintuitive purpose. Face-hardened armor, the type protecting battleship vital areas, was extremely hard on the surface but softer underneath. A pointed shell striking this armor would shatter because the hard nose contacted the hard armor face. The armor-piercing cap, made from softer steel, deformed on impact, creating a temporary cushion that allowed the shell body to penetrate the hard face without shattering. The cap itself disintegrated, having served its purpose of protecting the shell during the critical first microseconds of impact. The ballistic cap, a streamlined cone fitted over the armor-piercing cap, improved aerodynamics during flight. Naval shells traveled through the air for 30 seconds or more before impact. Air resistance during that flight reduced velocity and destabilized the shell, decreasing both penetration and accuracy. The ballistic cap reduced drag and improved stability, maintaining velocity that translated directly to penetration capability. The shell body cavity held the bursting charge, typically 48 to 110 pounds of explosive, depending on shell size and design philosophy. British shells used shellite, a mixture of TNT and picric acid. American shells used explosive D, a modified picric acid formulation. German shells used TNT. Japanese shells initially used shimose, a picric acid derivative, later switching to Type 91 explosive, a more stable formulation developed after premature detonations destroyed several Japanese ships during peacetime training. The explosive selection balanced power against stability. Picric acid provided maximum explosive power but was chemically reactive with steel, corroding the shell interior and potentially causing premature detonation. TNT was stable but less powerful. The various national formulations represented different compromises between these competing requirements. The British, emphasizing reliability after World War I experience with premature detonations, accepted reduced explosive power. The Japanese, emphasizing maximum destructive effect, accepted increased risk until combat experience forced doctrine changes. The fuse, perhaps the most sophisticated component, delayed detonation until after penetration. The base fuse design, standard by World War II, used mechanical inertia to activate after a specific time delay or after the shell had traveled through a specified thickness of material. The typical delay was 0.03 to 0.04 seconds, long enough for the shell to penetrate armor and enter interior compartments, but short enough to detonate before exiting the target entirely. The fuse mechanism was ingeniously simple. On firing, the massive acceleration armed the fuse by driving an inertia weight against a spring, aligning the detonator with the explosive train. On impact, deceleration released the inertia weight, which drove the detonator into the booster charge, initiating the explosive sequence. The timing was derived from carefully calibrated mechanical components that functioned reliably despite forces that peaked at 20,000 Gs during firing and 50,000 Gs during armor impact. The production process required industrial capabilities that only advanced economies possessed. The shell blanks were forged from specially alloyed steel under hydraulic pressure, generating thousands of tons of pressure. The forgings were machined to tolerances measured in thousandths of an inch. The heat treatment required precise temperature control and timing. The fuse assembly demanded skilled machinists working with components that had to function reliably under forces that would destroy any imperfectly manufactured part. The production volume was staggering. The United States alone manufactured over 150,000 16-inch armor-piercing shells during World War II. Britain produced comparable quantities of 14-inch and 15-inch shells. Germany, despite resource constraints, maintained production of heavy naval ammunition throughout the war. Japan's production, while smaller in absolute terms, represented an enormous proportion of national industrial capacity. The shells weren't just manufactured, they were tested. Each batch underwent proof testing, where sample shells were fired against an armor plate to verify penetration characteristics. The tests generated massive amounts of data about impact angles, striking velocities, armor thickness, and penetration probability. The data informed tactical doctrine about engagement ranges and aiming points that maximize hit probability and penetration likelihood. The terminal ballistics, what happened when shell met armor, were violent beyond civilian comprehension. A 16-inch shell striking at 2,000 feet per second delivered kinetic energy equivalent to approximately 80,000 foot-tons, the energy of a locomotive traveling at highway speed concentrated into 16 square inches of impact area. The impact generated temperatures exceeding 1,500 degrees Fahrenheit at the contact point, melting both armor and shell nose. The shock wave from impact propagated through the armor plate at supersonic velocity, potentially fracturing the armor even if penetration didn't occur. Successful penetration meant the shell punched through the armor plate, creating a hole slightly larger than the shell diameter, showering the interior space with armor fragments traveling at hundreds of feet per second, then continuing into the interior before detonating. The detonation, occurring inside the protected space, released explosive energy that couldn't escape through the thick armor that had been designed to keep it out. The result was overpressure that ruptured internal bulkheads, ignited ammunition and fuel, killed personnel through blast and fragmentation, and potentially triggered secondary explosions that could destroy the entire ship. The armor penetration tables that naval gunnery officers studied showed the brutal arithmetic. A 16-inch shell fired from 20,000 yards with a muzzle velocity of 2,500 feet per second would strike with a velocity of approximately 1,600 feet per second and could penetrate 17 inches of vertical face-hardened armor at a 90-degree impact angle. The penetration decreased with increasing impact obliquity and increased at range, creating complex trigonometry that fire control computers solved in real time during battle. The engagement in World War II naval combat typically ranged from 10,000 to 30,000 yards. At these distances, shells followed parabolic trajectories, climbing to altitudes exceeding 20,000 feet before descending at steep angles onto target decks. The deck armor, typically thinner than belt armor, became the vulnerable area at long range. The shells, striking nearly vertically, could penetrate deck armor and detonate inside machinery spaces, magazines, or fuel bunkers, where single hits could prove catastrophic. The Battle of the Denmark Strait demonstrated this terminal effectiveness with tragic clarity. Bismarck's 15-inch shells fired from approximately 16,500 yards descended at approximately 13-degree angles onto Hood's deck. The deck armor, 3 inches of steel over the magazines, was designed to defeat shells arriving at flatter trajectories from closer ranges. The steeply descending shells from Bismarck penetrated the deck armor as if it weren't there, detonated in or near the aft magazine, and triggered the catastrophic explosion that destroyed Hood in minutes. The Japanese experience at Midway, while involving bombs rather than shells, illustrated similar vulnerability. American dive bombers delivering 1,000-pound bombs that penetrated carrier flight decks and detonated in hangars filled with armed and fueled aircraft created the same type of internal explosions that armor-piercing shells were designed to produce. The carriers Akagi, Kaga, and Soryu were destroyed by internal explosions triggered by relatively small explosive charges detonating in exactly the wrong places. The largest naval shells ever manufactured were Japanese 18.1-inch rounds fired from battleships Yamato and Musashi. These shells weighed 3,219 pounds, contained 73 pounds of Type 91 explosive, and could penetrate 21 inches of vertical armor at 20,000 yards. The shells represented the ultimate expression of armor-piercing shell design, optimized for penetration against the most heavily armored American battleships that Japanese naval planning anticipated would be decisive in the Pacific War that never materialized in the form Japan expected. The engagement at Leyte Gulf, October 1944, saw Yamato fire her 18.1-inch guns in anger for the only time during the war. The targets were American escort carriers protected by destroyers and destroyer escorts. The massive shells designed to penetrate heavy battleship armor simply over-penetrated the thin-skinned escort carriers, passing completely through the ships and exploding outside, or failing to explode at all because the fuse delay was too long for the minimal thickness encountered. The irony was complete. The most powerful naval shells ever built were ineffective against targets they could theoretically destroy because the targets weren't heavily armored enough to trigger proper fuse function. The evolution of naval combat during World War II gradually reduced the relevance of armor-piercing shells. Aircraft carriers replaced battleships as the decisive naval weapon. Carrier aircraft, delivering bombs and torpedoes, could strike targets at ranges exceeding 200 miles, 10 times the effective range of naval guns. The massive industrial investment in armor-piercing shell manufacturing, the specialized steel mills, the heat treatment facilities, the precision machining shops, all of it became strategically obsolete as aviation dominated naval warfare. But the shells remained lethal. The few battleship engagements that occurred, Bismarck versus Hood, Washington versus Kirishima, Scharnhorst versus Duke of York, demonstrated that armor-piercing shells, when properly employed, could destroy even the most heavily protected warships. The mathematics and metallurgy that created these weapons remained valid, even as strategic circumstances reduced employment opportunities. The final battleship engagement of World War II occurred on October 25, 1944, when American battleships engaged Japanese forces during the Battle of Leyte Gulf. USS Mississippi fired the last 14-inch armor-piercing salvo in anger during the war, striking Japanese ships at night ranges. The shells performed exactly as designed, penetrating armor and detonating internally, demonstrating that the weapon system remained effective even as it became strategically irrelevant. Post-war analysis of naval combat revealed that armor-piercing shells had sunk or damaged approximately 50 major warships during the war. The number was smaller than pre-war expectations because aviation had dominated naval combat to a degree that pre-war planners hadn't anticipated. But for the ships that did engage in gun-to-gun combat, the armor-piercing shell remained the decisive weapon, capable of destroying any target if properly employed. The manufacturing infrastructure that produced armor-piercing shells was converted to peacetime production after 1945. The specialized steel mills, the heat treatment facilities, the precision machining shops all transitioned to manufacturing commercial products. The knowledge remained, documented in engineering textbooks and military technical manuals. The United States maintained limited production capacity through the Cold War, manufacturing armor-piercing shells for the Iowa-class battleships that returned to service in the 1980s, but the quantities were minimal compared to World War II production volumes. The final operational use of World War II-era armor-piercing shell design occurred in 1991 during the Gulf War, when USS Wisconsin fired 16-inch armor-piercing shells against Iraqi shore installations. The shells, manufactured in the 1940s and stored for 5 decades, functioned perfectly, penetrating fortifications and detonating as designed, demonstrating that properly manufactured and stored ammunition remained effective indefinitely, a testament to the engineering quality that had created the weapons 50 years earlier. The armor-piercing shell represented industrial-age warfare at maximum expression, the application of metallurgy, chemistry, physics, and engineering to create weapons of such sophistication that their development required national-level industrial capacity. No individual could manufacture an armor-piercing shell. The creation required steel mills, chemical plants, precision machining shops, testing facilities, and quality control systems that only industrialized nations possessed. The shells embodied national industrial capability, transformed into kinetic and explosive energy. The death ray never worked because physics wouldn't allow it. The Dauntless worked because mission-focused design mattered more than general performance. The American generals killed Axis soldiers through industrial superiority and sustained operations. The armor-piercing shell worked because 50 years of metallurgical development had solved problems that had defeated earlier ordnance engineering. And the shell that killed Hood in 3 minutes demonstrated what these weapons could achieve when design, manufacturing, and tactical employment converged perfectly. 79 years after Hood's destruction, the wreck sits in 9,000 feet of water, broken in half, a monument to 1,415 men who died when German engineering solved the problem of penetrating British armor with sufficient precision that a single salvo proved fatal. The shell that killed them, perhaps 2 shells, historical analysis remains uncertain, was manufactured in Germany, tested against an armor plate to verify penetration characteristics, loaded aboard Bismarck, and fired by crews trained in gunnery technique that maximized hit probability at extreme range. The engineering engineer who designed the shell never knew it would kill a ship. The steel mill workers who forged the blanks never knew their work penetrated Hood's deck armor. The machinist who assembled the fuse never knew it functioned perfectly after traveling 14 miles through the air and penetrating 3 inches of steel. The explosive chemist who formulated the bursting charge never knew it detonated inside Hood's magazine with timing precise enough to trigger secondary explosions. The industrial system that created the weapon was so distributed, so specialized, so compartmentalized that no individual could comprehend the complete weapon system from raw materials to terminal effectiveness. The armor-piercing shell existed at the intersection of science, engineering, and industrial capacity that defined total war. The weapons required advanced metallurgy that only decades of research had developed. They required explosive chemistry that only sophisticated laboratories could perform. They required manufacturing precision that only mature industrial economies could achieve. And they required testing programs that only wealthy nations could afford. The shells embodied national power measured in industrial output, and the nations that could manufacture them in quantity were the nations that could contest for global dominance. The shell that destroyed Hood weighed 1,764 pounds, traveled 26,000 yards in approximately 30 seconds, struck at approximately 1,800 feet per second, penetrated 3 inches of deck armor, and detonated inside the magazine with a bursting charge of approximately 50 pounds of explosive. The explosion killed 1,415 men, destroyed the most powerful warship in the Royal Navy, and demonstrated conclusively that offensive capability had exceeded defensive protection in the arms race between armor and armament that had defined naval warfare since ironclads had replaced wooden ships. The engineering that created that shell, the metallurgy that allowed penetration, the explosive chemistry that produced controlled detonation, and the fuse mechanism that delayed detonation after penetration all represented the most advanced ordnance engineering of the industrial age. The shell worked perfectly. It flew true. It penetrated, it exploded, and it killed with efficiency that designers had specified, but crews had hoped would never be tested in combat. The 1-ton explosive built to tear battleships apart did exactly what a mile-long engineering chain had designed it to do. It met armor that couldn't stop it, and it destroyed everything behind that armor through physics and chemistry that industrial civilization had spent 50 years perfecting. The monster shell that sailors prayed they'd never meet found Hood at dawn in the Denmark Strait, and 3 minutes later the prayers didn't matter anymore, because the ship was gone and the engineering had worked exactly as specified.